Hello, welcome to this video. Today we're going to talk about the volume of a paraboloid. And we're going to use this and going to find this formula, not with integration, although it's a good exercise for you. I suggest you maybe do it, but that's not how we're gonna do it. We're instead gonna do it using Cavalieri's principle. So first of all, before I go any further, this problem was suggested to me by someone named Yehuda Simcha Wildman, and he suggested me on the email, and that email he also featured a Desmos graph, which showed basically his proof, which, as he states, he discovered about 4 years ago.
Okay, so as you can see here, this is the Desmos graph that was sent by Yehuda Simcha Feldman, which basically shows the proof of the formula for the volume of a paraboloid. Now, I will obviously be proving what is stated here, and if you haven't realized it, the statement here is basically saying that the area of this cross section, like this circle, is the same as like the area of like this blue cross section here. It's like the difference between the two circles. So we're going to actually show that in the video. We're going to talk about more about Cavalieri's principle, but this also explains visually pretty well just like a more visual proof without words of this formula or how to find it. So yep, I'll also link the Desmos graph in the description so you can play with it. Okay, so wondering, there are a couple details here, but the parameters change are A, which is the radius of the paraboloid, the radius of the base of the paraboloid, B, which is the height, so A, which is the radius, B, which is the height, and H, which is the height of the cross section you're taking. Right, so those are the three parameters you're working with here. So, yep. Yes, so let's get back over to past me that'll actually show that the these two areas, this one and this one, are actually equal.
So what I'll be showing is basically a more detailed proof of what he did, but all credit goes to him. And if you also have any suggestions, you can um, send them to my email. I have my emails in the about section of my YouTube channel. I can also write down the description of this video. But now let's get into the problem. So first of all, let's talk about what Cavalieri's principle really is. So if I have two objects, say a cube, okay, so if I have like these two objects, Cavalieri's principle, if I have any two objects, this is just an example, Cavalieri's principle says that if you have a plane such that, so an infinite plane such that any plane that is parallel to this plane, when it crosses one of these objects, the area of the cross section is the same. So if I say have a cross section at the same height, if these areas are the same for any height, and the heights of these objects, so this length and this length from the top to the bottom, if these are the same, and the area of the cross sections are the same for any height, and the total heights are the same, then the entire volume is the same. right? So you can think of it as like moving this plane up and down, and when it crosses one of these objects, it has to cross the other, and with the same area of the cross section. If that is satisfied for some plane, then then their volumes are the same, which makes intuitive sense, right? Um, like if for any little sliver the volume is the same, then it makes sense that the entire volume is the same. And we're going to use this principle to find the volume of a paraboloid. So a paraboloid, if you don't know, is basically the generalization of a parabola. So a parabola, let's draw it. If we draw its equation, I'm just going to assume its point is it's like this, so it's just tangent to the x-axis at the origin. If this is a paraboloid, which if it's a paraboloid, then its function is y equals kx squared for some number k. In 3 dimensions, if you have in 3 dimensions, if this is the x-axis, this is the y-axis, and this is the z-axis, so right, and this paraboloid is like at the middle of, it's like tangent at the origin point to the xy plane, then its function is z equals k times x squared plus y squared for some k, right? So basically it means that the height is proportional to the distance in the paraboloid squared. So this is some length r. So you have a point of the paraboloid that it has a distance to the z-axis of r, and it has a height h. Then the ratio h over r squared is a constant. So this is constant. So that's what we're going to use, and so now let's try to use Cavalieri's principle to find the volume of a paraboloid. And now we understand what is a paraboloid and what principle we're going to use, which is Cavalieri's principle. So what we're going to do is take 2 objects. The first one will be an upside down paraboloid. And the second one will be a cylinder that is inscribing the same paraboloid when it's right side up, but it will have a hole the size of that paraboloid, right? So so this paraboloid is actually a hole in the cylinder. So if we take a cross section, then we need to like take the area of that entire circle minus the area of the paraboloid here. So this will be the area. This will be the non-existent area that we're going to have to erase from this entire area. So first of all, let's label things. So we want to take a cross section. Let's call the height h. So we're going to do the same thing here. This height will be h. Let's call this radius a. So the radius of this paraboloid will be a. And the entire height will be b. So on both sides, this height is b, this height is b. and this radius is A. So now we take a cross section at a height h. So let's measure the area of this cross section. So if we're at a height h and the entire height is b, that means that we're at a distance of b minus h from like the maximum of the paraboloid, which means that we know from the paraboloid that height divided by the radius squared is a constant. So if we call this radius r1, then we know that b minus h over r1 squared has to be the same as the entire height b divided by the large radius a squared. So this is equal to b over a squared. Or in other words, r1 squared is equal to a squared times, so b minus h divided by b is 1 minus h over b. And now, because we want the area of this, circle, right? So also I should mention that this cross section is a circle, and it's obvious because if we have some point at a distance r, then any other point at a distance r in the same height h will also have to be on the paraboloid from this definition, which will mean that we're making a circle that is parallel to the xy plane. So any cross section parallel to the xy plane will be a circle. So here, so we know that this is a circle, so its area is pi r squared. So we just need to multiply this by pi. And we get that the area of this cross section is pi a squared times 1 minus h over b. Now let's find the area of this cross section. So to do that, we're gonna do the entire area of the big circle, so like the area of the cylinder, and then we're going to subtract the area of the cross section of this paraboloid. Since remember, it's a hole, right? So in actuality, this looks like this. Well, not like this, if this was a circle. So it sort of looks like this, the cross section, and these two are circles, and this is a hole. So what we're gonna do is take the area of the entire thing, subtract the area of the hole, right? So the area of the entire thing is simple. It's pi a squared. Now to find the area of this hole, again, we're gonna mark this as a radius. Let's call this r2. So we know again, since now the height is h from the minimum point, we now have that h divided by r2 squared is equal to a constant, so it's also equal to b, the entire height, divided by the radius at b, which is a squared. So this is b over a squared. So r2 squared is equal to a squared times h over b. And now we want to subtract pi r2 squared, right? So we want pi a squared minus pi r2 squared. Well, if we substitute in r2 squared, we get minus pi a squared times h over b. And if we take out as a common factor pi a squared, we get pi a squared times 1 minus h over b. And we can see that these are the exact same. Meaning that if we take any plane that is parallel to like the xy plane of the paraboloid, and we look at the cross sections, these have the same area, meaning that the volume of this paraboloid is the same as the volume of the entire cylinder minus the volume of the same paraboloid, right? This is the paraboloid just upside down, they obviously have the same volume. So if we label the volume of the paraboloid as draw a little paraboloid here, this, which will represent the volume of this thing, will be the volume of the cylinder. minus the volume of the same paraboloid, right? We use these paraboloids are the same, just upside down, which means that the volume of the paraboloid is half that of the cylinder. But we know how to evaluate the volume of a cylinder. It's the area of the base, which is pi a squared, times the height, which is b. So this is 1/2 pi a squared b. And that's the formula. So if you have a paraboloid with height b, and at the top the radius is a, then its volume is just half that of if it was a cylinder, which is half pi a squared b. So, and if you have something in the form of z equals kx squared plus y squared, and you want to look at it like that, then you can say, well, this constant is actually the constant k. So we know that b will be divided by a squared will be k. So in other words, a squared is equal to b over k. And then we can also substitute that in to get that this is half of pi b squared over k. So these are like two ways to represent the volume of the paraboloid, depending on depending on like which one is better in that situation. But that's the formula. And again, thanks to Yehuda Simcha Vedman that suggested this to me. And finally, that's it. For more content like this, please subscribe to my channel. I'm uploading more interesting problems and things like this in the future. And finally, that's it.